Good afternoon, students. Today let me learn zone refining. Zone refining method is based on the principles of fractional crystallization. According to this fractional crystallization, the impurity metal is taken in the form of a rod. One end of the rod is heated using a mobile induction heater. Okay, so impurity metal rod heated by mobile induction heater. That heater we can move place to place. Okay, which result in melting of the metal on that portion of the rod where heated at that portion of the impurity metal rod melt. Okay, so when the heater is slowly moved to the other end of the metal rod, impurities will move on to the adjacent molten zone formed due to the movement of the heater. Okay, so we are taking the impurity metal rod, one of the end heated by mobile induction heater. At that time that impurity metals started to melt, then move to the mobile induction heater to the other end. Okay, as the heater move further away, the molten zone containing the impurities also move along with it. That impurities also move along the heater. This process is repeated several times by moving the heater in the same direction again and again to achieve the desired purity level. That impurity metal rod converted into purity metal rod. Okay. So this process is carried out in an inert gas atmosphere to prevent oxidation of metal. Okay, this process, this fractional crystallization process is carried out in an inert gas atmosphere. Why we are using the inert gas atmosphere? Because to prevent oxidation of metals. Elements such as germanium, silicon and gallium that are used as a semiconductor are refined using this process. In this process we are using the semiconductors. Semiconductors example germanium, silicon, gallium. So the next method is a vapor phase method. Vapor phase method, the metal treated with a suitable reagent which can form a volatile compound with metal. Okay, so here we are using the suitable reagent. It will form the volatile, easily evaporated metal. Only we can use. Volatile compound is decomposed to the pure metal. Okay, so the vapor phase method, first process is a Mond process for refining nickel. Nickel is purified by Mond process. Okay, so the impure nickel is heated in a stream of carbon monoxide at around 350 Kelvin. Okay, so the impure metal heated with carbon monoxide, stream of carbon monoxide at 350 Kelvin. The nickel reacts with the carbon monoxide form a highly volatile nickel tetracarbonyl. The solid impurities left behind. Okay, so that vapor volatile impurities, volatile compound is a nickel tetracarbonyl. Then on heating the nickel tetracarbonyl around 460 Kelvin, the complex decomposed to give purity nickel. Okay. The next process is a Van Orgel method for refining zirconium or titanium. Van Orgel method is based on thermal decomposition of metal compounds by heating, okay, which lead to the formation of pure metals. Titanium and zirconium can be purified by using Van Orgel method. Example, the impure titanium metal is heated. Impurity, that titanium metal is heated in an evacuated vessel with iodine at a temperature of 550 Kelvin to form a volatile titanium tetraiodide. The impurities are left behind. They do not react with iodine. Okay, that titanium, impurity titanium, we are taken and reacted with iodine. Okay, so the impurities are left behind. That purity titanium is evaporated. Okay, volatile titanium tetraiodide is evaporated. The purity titanium only react with iodine. The volatile titanium tetraiodide vapor is passed over a tungsten filament at a temperature of around 1800 Kelvin. The titanium tetraiodide is decomposed to titanium and iodine. Okay, so that titanium is deposited on the filament, tungsten filament. Okay, so the iodine is reused. The next let we learn application of metals. First one, application of aluminum. Aluminum is the most abundant metal and good conductor of electricity. We know aluminum metal. Okay, so this aluminum is the most abundant metal. It is a good conductor of heat and electricity. It also resists corrosion. Okay, so many heat exchangers or sinks and our day-to-day cooking vessels are made up of aluminum. Cooking vessels, daily cooking vessels are made of aluminum. It is used as wraps and is used in packing material for food items. Okay, this aluminum also used for packing material for food items. Aluminum is not very strong. It alloys with copper, manganese, magnesium and silicon are lightweight and strong. It is used in design aeroplane and other forms of transport. This aluminum alloys are used to design aeroplane and other forms of transport. Aluminum shows high resistance to corrosion, so it is used to design of chemical reactors, medical equipment, refrigeration, gas pipelines. Okay, so aluminum is a good electrical conductor and cheap cost. So hence it is used in electrical overhead, electrical cables and steel core for strength. So next one, application of zinc. Metallic zinc is used in galvanizing metals such as iron and steel structure to protect them from rusting or corrosion. Okay, metallic zinc is used in galvanizing. Galvanizing means that one metal covered with by another metal. Okay, it is protect them from rusting and corrosion. Zinc is also used to produce die castings in the automobiles, electrical and hardware industries. It is used for castings purpose. Zinc oxide is used in the manufacture of many products. It is used to manufacture by paint, rubber, cosmetics, paramedicals, plastics, battery, textiles, etc. Okay, so brass is an alloy of zinc. It is used in water valves and communication equipment. It is a high resistant of corrosion. Okay, so one of the alloy of zinc is brass. That brass is used in water valves, communication equipment, instrument and is used in high resistant of corrosion. Next let we learn application of iron. Iron is one of the most useful metal and alloys are used in everywhere including fridge, electricity, pylons, bicycle chains, cutting tools and rifle barrels. Cast iron is used to make pipe, walls, bumps, stoves. Okay, so these materials, pipe, walls, bumps used to make cast iron. Then magnets can be made from iron and it alloys and compounds. An important alloy of iron is stainless steel. Okay, stainless steel is an alloy of iron. It is very resistant to corrosion. It is used in architecture, bearing, cutlery, surgical instrument, jewelry. etc. Nickel steel is used for making cables, automobiles, aeroplane. Nickel steel is a alloy of iron. Chrome steel is used for manufacture cutting tools, crushing machines. Okay, next let me learn the application of copper. Copper is the first metal used by the human, and extended use of its alloy bronze reached in new era bronze age. Okay, so first metal used by the human is a copper. Copper is used for making coins, ornaments, gold, and other metals. Okay, ornaments making along with the gold and other metals. Copper and alloy is used for making wires, water pipes and other electrical parts. Next one, application of gold. Gold is the one of the expensive and precious metal. It is used for coins, okay, and can be used as standard for monetary system in some countries. It is a extensively jewelry in its alloy formed with copper, okay, with gold mixed with copper, then they will used to make ornaments. Then it is used for electroplating to cover other metals with a thin layer of gold. Watches, artificial lamp joints, jewelry, dental filling, their purpose are used. Then gold nanoparticle are also used for increasing the efficiency of solar cell and used as a catalyst. Next, let me learn p-log elements. We know the periodic table. 4 types of periods are there. S-log elements. Totally 4 blocks elements are there. S-log elements, p-log elements, d-log elements and f-log elements. Okay, already we studied S-log elements. Alkali metals and alkaline earth metals. Okay, so in this we study p-log elements. Okay, so p-log elements 13th to 18th group elements are called p-log elements. Okay, so these elements boron, carbon, nitrogen, oxygen, fluorine, helium respectively. That is 13th group. That p-log elements are 13th group to 18th group in the modern periodic table. The most abundant metal is aluminum, and that aluminum and it alloy have plenty application ranging from household purpose. Then semiconductor materials, that is semiconductor silicon, germanium, that also we will study in p-log elements. So first let me learn general trends properties of p-log elements. Okay, first that p-log elements electronic configuration. We want to learn the electronic configuration, general trends, electronic configuration, size, ionization enthalpy, electronegativity. Okay, first let me learn electronic configuration and oxidation state. p-log elements general electronic configuration is ns2 np126. Okay, ns2 s orbital, ns2 only s orbital occupy only 2 electrons, so ns2. np126 p orbital occupy n1 to 6 electron. The elements of each group have similar outer shell electronic configuration and differ only in the value of n. So in this p-log elements outer similar electronic configuration only that differ in the n value. N means principal quantum number. The elements of group 8 Inert gases 18. 18th group elements are inert gas. That group elements completely filled p orbitals. So that 18th groups are more stable, but it is a less reactivity. Then p block elements variable oxidation state. Highest oxidation state is equal to the total number of the valence electron present in the group. S block elements, we know it is a positive oxidation state and only 2 electrons. P block elements show negative oxidation state also. The halogens strong tendency to gain electron to stable halide ion completely filled electronic configuration, so that halogens have -1 oxidation state. See the tabular column. 13th group name is isogens. 14th group tetragens. 15th nictogens. 16th chalcogens. 17th halogens. 18th inert gas. General electronic configuration 13th group NS2 NP1 13 3. So NS2 NP1 2 plus 1 3. 14 4 NS2 NP2. 15 NS2 NP3 5 S2 P3. So 2 plus 3 5. 16 NS2 NP4. 17 NS2 NP5. 18 NS2 NP6. Okay, highest oxidation state 13th group plus 3 oxidation state, 14th group plus 4, 15th group plus 5, 16th group plus 6, 17th group plus 7, 18th group plus 8. Other oxidation state are 13th group, maybe it have the plus 1 oxidation state, 14th group plus 2 and minus 4, 15th group plus 3 and minus 3, 16th group plus 4 plus 2 and minus 2, 17th group plus 5 plus 3 plus 1 minus 1, and 18th group plus 6 plus 4 and plus 2. So the next general trends and property is a metallic nature. The tendency of an element to form a cation by losing electron is known as electropositive. That element lost the electron, it will form electropositive or metallic character. So this character depends on the ionization energy. Generally on descending a group, the ionization energy decrease, metallic character increase. So that ionization energy decrease in the groups, metallic character increase. Okay, so these are the P block elements. 13th group elements boron, aluminum, gallium, indium, thallium, nicotinium. 14th group carbon, silicon, germanium, tin, lead, fluorovium. 15th group nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. 16th group oxygen, sulfur, selenium, tellurium, polonium, livormonium. 17th group fluorine, chlorine, bromine, iodine, astatine, tennessine. 18th group helium, neon, argon, krypton, xenon, radon, oxygen. Okay, so these are the P block elements. So these P block elements contain metals, metalloids, non-metals, and radioactive metals. In P block elements present in lower left part of the metals, while the elements in the upper right part are the non-metal. Lower part is metal, upper right part is non-metals. Elements group 13 have metallic character except the first element. Okay, so this 13th group elements except first one remaining all metallic character. Okay, the boron is a metalloid. The first one, that green, is a metalloid. All the green elements are metalloid. The blue color is a metal. Purple color, violet color is a non-metals. These all radioactive. The atomic radius of boron is very small. It has relatively high nuclear charge. Atomic boron, very small atomic radius, but the nuclear charge is high. Okay, so it has the non-metallic character. Non-metallic character increases in group 14 elements. Carbon is a non-metal. In the 14th group, carbon is a non-metal, while silicon and germanium are metalloids. Silicon and germanium are metalloids. 15th, nitrogen and phosphorus are non-metal. Arsenic and antimony are metalloids. In group 15, nitrogen and phosphorus are non-metal and arsenic and antimony are metalloids. 16th group, oxygen, sulfur and selenium are non-metal. Tellurium is a metalloid. 17th and 18th group are non-metal. Next, let we learn ionization enthalpy. As we move down a group, generally decrease in the ionization enthalpy of element. Okay, so in the moving down top to bottom, the ionization enthalpy decrease due to increase in atomic radius. In p block elements, there are some minor deviation in the general trend. In group 13, boron to aluminum, the ionization enthalpy decrease. Okay, in 13th group, boron to aluminum, the ionic enthalpy decrease. From the aluminum to thulium, marginal difference. Okay, this aluminum to thulium, marginal, very less deviation only. This is due to presence of inner d and f electron have very poor shielding effect and compared to s and p electron. Okay, because of the effective nuclear charge, valence electron increase. Okay, so that 15th and to 18th follow general trend. In these groups, ionization enthalpy decrease as we move down the group. 15 to 18, as we move down the group, ionization enthalpy decrease because the poor shielding effect of d and f electrons. So the next one is electronegativity. As we move down the 13th group, the electronegativity first decrease from boron to aluminum. Electronegativity decrease from 13th group, boron to aluminum, first and second element. Okay, then marginally increase from helium. Okay, so the next, from the third element, it will, electronegativity will be increase. Okay, so 14th group also, first two elements decrease then increase. Okay, so the next one, anomalous properties of first elements. In p block element, the first member of each group differ from the other element of the corresponding group. So the following factor responds for the anomalous behavior. The first one is a small size of the first member. The anomalous properties of the elements, the first point is a small size of the first member. Second one, high ionization enthalpy and high electronegativity. Okay, so the anomalous properties, small size, high ionization enthalpy, high electronegativity, then that absence of d orbital in the inner valence shell. Two more question. What are the anomalous properties of the elements? That is 3 points. Small size of the element, First member, high ionization enthalpy and high electronegativity, absence of d orbital in their valence shell. The first member of the group 13, boron is a metalloid, while other are reactive metals. So 13th group, first element is a metalloid, others are reactive metal. Boron shows diagonal relationship with silicon. Silicon is a 14th group. It is 13th group boron, diagonal relation with the 14th group silicon. The oxides of boron and silicon similar to their acidic nature. So this boron and silicon form covalent hydrides. Group 14, the first element is a carbon. Carbon is a non-metal. Other metal elements are metalloids. Metalloids are silicon and germanium. Then metals, tin and lead. Other elements of the group carbon can form a multiple bond. This carbon only form the multiple bond. So the carbon have the tendency to form a chain of bond. So this carbon chain is called catenation. There is considerable decrease in the catenation property down the group. As we move down the group, the catenation decreased. In the 15th group, first element nitrogen, it is different from the other element. Carbon and nitrogen can form multiple bond. Nitrogen is a diatomic gas, unlike the other member of the group. Similarly, group 16, the first element oxygen, it exists as diatomic gas. Diatomic means O2 form. Due to high electronegativity, it form hydrogen bond. In 17th group, the first element is a fluorine. The fluorine is the most electronegative element. So behaves quite differently compared to the rest of the members of the group. Like oxygen, it also form hydrogen bond. Fluorine form hydrogen bond, but fluorine have the -1 oxidation state. Other halogens are plus oxidation state. Okay. Fluorine is the strongest oxidizing agent and has the most reactive element among the halogens. Next, let we learn inert pair effect. So we know alkali metals are +1 oxidation state, alkaline earth metals are +2 oxidation state. This alkali and alkaline earth metals are S block elements. Okay, so similarly P block elements also show the oxidation state. So oxidation state based on the valence electrons. Okay, so these P block elements also have variable oxidation state. So in the group 13 to 16, as we move in 13th group, as we move from boron to heavier element, there is increase in tendency to have +1 oxidation state rather than the group oxidation state +3. Example, aluminum. Aluminum have the +3 oxidation state. It is more stable than aluminum +1. Well, titanium +1 is more stable than titanium +3. Okay, so aluminum 3 chloride is stable, whereas thallium 3 chloride is highly unstable. Okay, so some +3 oxidation states are stable, +1 oxidation states are unstable. Okay, this shows thallium is the stable lower oxidation state, correspond to the loss of Np electron only and not Ns electron. Okay, this stable lower oxidation state correspond to the Np and Ns electrons. Heavier post transition metals, the outer S electron have a tendency to remain inert. show the resultant to take part in the bonding, which is known as inert pair effect. Okay, heavier post transition metal, that outer electrons are act as a inert, so it to take part in bonding, so it is, this effect is called inert pair effect. Okay, so next let we learn allotrophism in p block elements. Some element exist more than one crystalline or molecular forms in the same physical state. Example, carbon exists as diamond and graphite. We know allotrophism, different forms of the elements, carbon, diamond and graphite. And this phenomenon is called allotrophism. So allos means another, trophy means change. Different forms of an element are called allotropes. P block elements of allotrophism. Okay, see the tabular column. Boron allotropes, amorphous boron, alpha rhombohedral boron, beta rhombohedral boron, gamma orthorhombic boron. Carbon allotropes are diamond, graphite, graphene, fullerene, carbon nanotubes. Silicon, amorphous silicon, crystalline silicon, germanium, alpha germanium, beta germanium, tin, gray tin, white tin, rhombic tin, sigma tin. These are the allotropes of elements. Phosphorus, white phosphorus, red phosphorus, scarlet phosphorus, violet phosphorus, arsenic, yellow arsenic, grey arsenic, black arsenic, antimony, blue, white antimony, yellow, black, oxygen, dioxygen, ozone, sulfur, rhombus sulfur, monoclinic sulfur, selenium, red selenium, grey selenium, black selenium, monoclinic selenium, tellurium, amorphous and crystalline. These are the allotrophism elements.